we'll just start, and if someone is late, then
it's going to be recorded, or they will record it from Oslo?
Yes, it's being set up to record from Oslo, and you have a say in how it gets published or so.
I mean, just publish everything, yes.
Okay, well, anyway, let's begin. So, welcome everyone to the seminar. Today's speaker is Luca Frediani, and his talk has the title, "The Basis Set Limit is no longer a chimera. DFT energy and properties with multiwavelets." So, please go ahead, Luca.
Thank you. I thought about sharing some of the new results we got in the last year that concern mostly energies, because we've done a big test set of calculations showing how good we are at computing energies to the basis set limit and how bad the others are doing. Since anyway this was going to be recorded, I thought I would also give some introduction. I apologize for those who have seen it before, so some introduction about multi-wavelets. I'll try to be pedagogic and not too detailed in the exposition. So this is my outline. I'll talk a little bit about multi-wavelet theory, what it is and what it's about. Then we will...
there's no reason to turn off the lights.
We will then...
Fine as it was.
We will then... I will touch briefly upon how the code we have is structured, and then talk about the two main things we have, which are like calculation of Kohn-Sham DFT with multiwavelets, and a little bit on response property, especially magnetic properties. This is so far the group of people who have worked or are working with this, and mostly now involved are Stig Rune, Krylov for the mathematical part, Peter Wind on the implementation, Dan Jonsson for some technical support at the HPC. And then we have also two master students who are not mentioned here. Magna, who is about to defend his master thesis, and Rune, whom I not see here, who will hopefully be ready during the year. So, yes. So just some introduction. These are shielding constant for magnesium oxide calculated at Hartree-Fokker and B3LYP with some of the best basis sets available. And I would like to draw your attention, for instance, at oxygen calculated with this augmented set of bases that goes, for instance, for Hartree-Fokker from 36,000 to 60,000 to 10,000 to minus 69 to minus 20 to minus 17. And it's not as erratic with B3LYP, but it's still not very well converged. You can see it goes from 3,000 to 2,500. So how converged are these results? How much would you trust these numbers? So of course this raises question, and this augmented CS4 is really something, is a big basis set tailor-made for magnetic properties. So in a sense, it's some of the best things you can do when it comes to magnetic properties. So would you trust these numbers? So this is our basis set from Frank Jensen. So, and this is, for instance, a parametrization of one of the, it's not the same basis set, but it's one of the largest basis sets. I want to draw your attention to how much work there is into parametrizing these basis sets. And yeah, this is the basis, and continues, and continues, and yes. So this is how much it takes to parameterize augmented quadruple zeta for basically the first and second row elements only. So forget about using these bases for anything bigger than that when it comes to atoms, okay? And this is the parameterization for the multi-wavelet basis set. Hold on. There. Okay? So this is all we need. All we need is just to set up the precision we want for our calculation. So, and that would be regardless of which atoms we are considering on top. Just a nice picture to have a break. And something about multiwavelets. I'll drop the mathematical part. I'll tell you very briefly that multiwavelets is just a complicated way of saying that we're using polynomials. Okay, so these are polynomial functions, as you can see here, depicted up to third degree, so constant, linear, quadratic, cubic. And then you can start doing things with them. You can start making them smaller and represent them in smaller intervals and refine your representation to smaller and smaller intervals until you get something you're satisfied with. The multi-wavelets are functions that are constructed as a orthogonal complement to the scaling function, so they are not polynomials, but they are piecewise polynomials. So they are combination of polynomials on one side and on the other. What is the role of these multi-wavelet functions? The role of the wavelet functions is to tell you how good or how bad your representation is. So if you are trying to represent a function, you are using polynomials to represent that function, but to tell you whether that representation that you got is good or not, you use the wavelets. So this is just giving you the measure of how good or how bad your representation is. And that tells you whether you can build a better representation, or you have to build a better representation given the precision requirements that you have set up, or not, or if you can be satisfied with what you have. Some properties that are very nice. You can achieve completeness in the L2 sense, both increasing the order of the polynomial and by increasing this refinement that you perform. They are all orthonormal. They all have disjoint support. So each function lives in a certain interval, and once that interval is comes to the end, then it comes to zero. It's by definition zero. So it's trivial to take scalar products because you only have to deal with functions that are in the same interval. Another extremely important property that we build very much upon is the vanishing moment. So the fact that for the wavelet functions, the integral of the wavelet function with polynomial, so here's a monomial up to a given order, is 0, which is the same order as the polynomial basis. So if you have a polynomial basis of order 10, any polynomial up to order 10 will give a vanishing integral here. This is a key property to lead to fast algorithm because it will give you sparse representations of functions and operators. Okay? So when you have sparse representations, then you can optimize your calculations much more. Again, this joint support is also a very important property because that tells you that you don't, if you want to represent a function, let's say on the right side here, you don't need to bother about what happens on the left side. Which means that, okay, if this representation is good enough on the left side, I can stop. If it's not good enough on the right side, then I can continue. But that will not affect what happens on the left side, meaning that this adaptivity is then straightforward. I can refine only what I have to be, and I don't have to bother what happens to the side where I didn't refine. Without this joint support, meaning if functions start overlap in between integrals, of course, if you refine on one side, you would influence what happens on the other side. And that will complicate your picture significantly, also your algorithms. Then just an illustration how good things can be done. You see this is a, let's say, a Slater orbital, say with a cusp. And this would be the first representation we get if we use just a minimal set of polynomials. But then we say, okay, this is obviously not good enough. And then we can refine and go on. Still not good enough, but getting better. Still not good enough, but getting where we have to go. And the final one is really quite good, and then you see the difference. The difference is then almost 0. And of course, you can refine depending on the threshold you decide. You can do it in several dimensions. Here in 3D, of course, we need 3Ds. And this adaptivity is a key property to be able to represent things in 3D, because if you were to refine all your space uniformly like that with a uniform grid, then the curves of dimensionality would prevent you from performing larger calculations, because this would take up too much memory and too much resources. Yet another picture to give you some break. And now we go for something about the code. We're using a combination of Python and C++, CMake for combination, and Doxygen for documentation, in theory, Doxygen. In practice, nothing. But that's a different story. Libraries, we use Eigen3 because many of the things we have to do deal with small matrix multiplies and matrix vector manipulations. So Eigen3 is really a very good choice to make both the coding and faster and easier, and also to boost the performance as well. We used to use some boost libraries, but now they're almost out of MRChem because we realized that boost libraries are very heavy, and it's not that you can cherry pick whatever you need, but you need to take the whole bundle, and that is some, I don't know, 2 gigabytes of libraries. And if you only need just a few, that's really not the way to go, because then you end up with a lot of problem compiling and so on. For DFT, we use XCFun for density functionals, and MPI and OpenMP, mostly OpenMP so far for parallelization. We are working on better MPI parallelization, which is not ideal so far. We have 3 libraries, now actually 2, one for functions and operators, and one for the chemistry part, where we do like XCF, properties, orbitals, densities, all the overlay to deal with chemical parts. Currently, we can do parallel linear scaling of Poisson and Helmholtz operator application. We can solve Hartree-Fock and Kohn-Sham equations. We still have some issues with scaling of the exchange when it comes to Hartree-Fock and Kohn-Sham. It's not scaling linearly, scaling quadratic so far. Of course, we use XCFun, as I said. For now, we have electric and magnetic linear response properties, and there's also a pilot implementation of orbital free density functional theory. Why this popped up, I don't know. Okay, and yet now Trunso by night picture, and we go on to Kohn-Sham density functional theory. So you all know the slightly rewritten by moving the potential on the right side and the expectation value or the eigenvalue on the other side, which is sort of a way to reformulate this into a Green's function problem, because I know the Green's function of this operator here is known, and then you can rewrite the Kohn-Sham equation into an integral formulation. What is the advantage? The advantage is that for multiwavelets is that multiwavelets are really good for dealing with integral operators. They're not as good to deal with differential operators. So this formulation allows us to have very robust and stable convergence. I will not bother you with the details here too much. So this is just to show you the convergence. That this is the standard convergence of the integral equation without any acceleration, and then we perform an acceleration which is in spirit similar to the DIS. It's called Krylov accelerated inexact Newton method, and you can see that it leads to significant boost of the performance in the number of iterations. Now for some calculations. So because I want to focus more on results today than on the theory. As you can see here, we have started looking at some energy benchmarks. On the left side, these are LDA calculations performed with MRChem, so multiwavelets, and that's the blue line. And then we have, as a comparison, we have a augmented plane wave code, ELK. We have a numerical atomic orbital code, Fij AIMS, and then we have a standard Gaussian type orbital code. In this case was used, NWChem was used. And what you see here in the graph is the error that we get, or the difference we get with respect to the NIST, NIST standards that are numerical standards to for these atoms. In this case, these standards are available for closed shell atoms, because in that case you can perform the integration in 1D, and it's closed shell, and it's spherically symmetric. So closed shell maybe not, but it's definitely spherically symmetric. So as you can see, the blue line, that is the multi-wavelet code, is consistently below 10 to the minus 6 Hartree. So that is less than 1,000th of a kcal, so a calorie in a sense. Then the next best is this numerical atomic orbitals. That is, as you can, what we normally call chemical accuracy here is 10 to the minus 3, because that's a milli Hartree. That's roughly 1 kcal per mole. So keep this in mind. So these numerical atomic orbitals, they still are able to deliver very well below chemical accuracy, but they are not for all atoms they are as good as multiwavelets. Okay? Then there's a little bit of a mixed picture between ELK, which is the plane wave code, and WCAM, which is Gaussians. As you can see, Gaussians are good in the beginning, but their main problem is indeed grows with the atomic number. As you can see, the error grows with atomic number. So Gaussians, and that is clearly related to the cusp. So the more important the cusp becomes when you go to higher atomic numbers, the more problematic it is to represent things with Gaussians. So then for LDA we had this NIST standard, but this was to some extent the main point was to show that we can trust the multi-wavelet numbers. So on the right side, what you will see is the calculation performed with Gaussian type orbitals and numerical atomic orbitals compared to multi-wavelets. There are no augmented plane waves here because we didn't manage. So they didn't manage, those that run the calculations, it was not us, to perform equally well. So we had to drop those calculations. As you can see, the numerical atomic orbitals are able to consistently get you below chemical accuracy, but not the Gaussians. The Gaussians at some point go beyond that. Those two spikes, those two like sort of hills that you see here, they are lithium and beryllium, and then sodium and magnesium, if I remember correctly, because the basis set we have used, which is augmented quintuple zeta, is not available for those atoms. So there we have to use augmented quadruple zeta, and you see the effect. So it's not huge, but it's still significant. So it's so that brings you away from the standard trend. Okay, so let's go on to molecules. So we have taken a test that comprises the G2 test set, which is 147 molecules, plus some more for a total of 211 molecules. And we have compared different calculations performed with numerical atomic orbitals on one side and Gaussian type orbitals with increasingly larger basis sets. So for the numerical atomic orbitals, it's this 4 set called light, tight, and tier 2 and 4. For the GTOs, what you see here is all the correlation consistent basis set from double zeta to quintuple zeta. Okay? And these are the absolute energies, and keep in mind again that chemical accuracy is at this 1 here. That's the level where we have chemical accuracy. So in a sense, and we have collected here the maximum absolute error, maximum absolute deviation, root mean square deviation, and then the maximum error for each set. As you see, they consistently go down. Again, what we see is that the numerical atomic orbitals are indeed better at delivering the accuracy, so there's obviously an improvement also on the Gaussian type orbital side, but it's not as marked as the numerical type orbital. Then the next step is to look at atomization energies. So those were total energies, so just the absolute value of your final SCF calculations. But then normally in DFT, what you are interested in, especially when you benchmark the DFT calculation, is atomization values. So what is the difference between molecular energy and the corresponding atoms? As you can see, all basis sets perform a little bit better. So if you see here the difference, and especially Gaussians, if you look at sort of the animation here, especially Gaussians, they benefit quite a lot by error cancellations. So multiwavelets don't benefit at all from error cancellation because whatever is below certain accuracy is for us noise. So there's really no cancellation, just random numbers. Numerical atomic orbitals, they benefit a bit. So it's not that clear graphically here, but what I can tell you is that this is a logarithmic scale. So what you get is, with numerical atomic orbitals, is like the agreement with multiwavelets becomes 1.52 times better. For Gaussians, it can go up to 8 times. So if you had an error of 10 kcal, it can go down to 1.52 kcal on average. So it really has a huge cancellation effect. Last thing, dipoles. So just to have a look at something that is not variational, because the energy is to some extent easy because it's quadratic in the variation of the orbitals. So when you're converged, you have a very good, you have a very small error because the error is quadratic in your variation of the orbitals. But that doesn't apply to properties, for instance. That's not apply to dipole moments. So how good are dipole moments? And here you can see that, for instance, both, if you set like a very low bar and you set, let's say, okay, I want an accurate dipole moment compared to the basis set limit that is close, so it's less than 0.01 kcal with, dBi to the basis set limit. Only the biggest basis set are able to deliver that. So on average, so only the tier 4 for the numerical atomic orbitals and quintuple zeta for GTOs, but still there are quite significant outliers on both sides. So on both sides you see that there's something that there are some molecules that where the dipole moment is not converged to more than 0.1 dBi with respect to the basis set limit. And the difference between left and right, I forgot to say, is on the left you have PBE and on the right you have PBE 0. But the trends are very, very similar, so you can superimpose, you can just draw the same conclusions for both functionals. So it doesn't really matter much if you have exact change or not. Then we got recently the referee report for this work, and we had to please the referee, who asked for a huge amount of extra basis sets to be run. That if we had to run all the calculations he asked for was some 5,000 calculations. Luckily, we were able to run I don't know, half of them, what he suggested. There are several kinds of basis set now, so you see the Popel kinds of basis set, this PC2 and PC3, which is the same family that I was showing the result for concerning the magnetizabilities, and then just for comparison, triple and quadruple zeta, and then this DEF2 triple zeta and quadruple zeta basis sets. I will not spend too much time telling you about the details. I just want to tell you that the best when it comes to the energy is definitely this PC3. So PC3 is really able to deliver very well and very good energies. So although it's in size, I assume comparable to triple zeta, it delivers results that are comparable to quintuple zeta. Is it not triple zeta? It's already quadruple. Okay, PC3, it should be roughly in size as big as a quadruple zeta, but it has it gives results, it delivers results that are better than quintuple zeta. So it's a really good basis set for energies. Again, here you see the huge cancellation effects that you get when you go to atomization energies. So luckily so, to some extent, not so luckily for us. But in a sense, this is the first time that we are able to quantify with certainty how much is this cancellation. So that was just speculation so far. Now we can tell you that this is as much. And here is the dipole moment. I just want to draw your attention to one feature here. As you can see, this PC3 is really good for energies. But as soon as you look at dipole moments, then you see that having augmented functions will win. So they are not as good. So in a sense, there's a lot of work going on to parameterize basis functions, but all this work is very often tailor-made to a given property. So either to give you good energies, or to give you good properties, or to give you good, I don't know, good polarizabilities or good magnetizability. So in a sense, the picture you get can get skewed to some extent. And now, for instance, this for the dipole moment, it looks like that this for def to quadruple zeta is definitely the best among those observed here.
This is now basically the result of a large number of calculations
Yes.
for different molecules.
Yes, it's 211 molecules. This is the maximum absolute deviation and the root mean square deviations.
And mostly very small molecules, or
Yeah, and this is G2s as set. So the biggest one when it comes to number of electrons is silicium tetrachloride. That is some 84 electrons. Yeah. Some northern light for those that are not in Tromsø and cannot appreciate it live. And then we go for response theory. So one very nice feature of working with multi-wavelets is that it's really true to the theory. So what you see is what you get. In a sense, when I'm coding something with multi-wavelets, this is really what I see. So I have an orbital, and I really have an object in my code that is the orbital. So I don't have a representation in terms of a set of basis functions or like the atomic orbital coefficients. And then I have the true Fock operator, which I can directly apply and see what happens. And this is equal to applying the Fock matrix to the set of my orbitals. So this is just the usual Kohn-Sham equations that we then reformulate in this integral form to solve. And then you just perturb this. So you just add a small perturbation, and what you get is an analogous equation that now gives you the perturbed set of orbitals. So you see the features of the equations are similar. So here you have the orbitals, you have this Green's function, and then you have the potential applied to the orbital, and then something that depends on the Fock matrix. Here again you have the perturbed orbital, so the variation of the orbital, the Green's function, the potential applied to the perturbation, the Fock matrix applied to the perturbations, plus one term that contains the perturbed Fock matrix. So you have this extra third term that otherwise wouldn't appear. And this is exactly what you code. So there's nothing else in a sense. I'll skip this. So we computed magnetizabilities and shielding like that. And yeah, I'll skip this one too. Some tests about polarizabilities to see that things are working very well. Again, I think I can skip this. Magnetizabilities, I think I've shown you these values before. The main point of these numbers is to show you that with multi-wavelets we are able to converge very well, and also that is the case for Gaussians. You see that the agreement when we go to sextuple zeta is very good, but I want to point out that when you get to sextuple zetas, this calculation with multi-wavelets becomes indeed faster, because this is a huge basis set, and at this point we're able to deliver also better performance. But another point I would like to raise here is that the automatic gauge invariance. So if you now take the same calculations and do not use gauge invariant atomic orbitals, then sextuple zeta is not that good anymore. So this is what and the reason is obvious, because you have a huge cancellation here, and then you get an error due to this cancellation. So 4288 becomes 4317 here, which is the best you can do, and here we are still at 4288 with multi-wavelets. So we are much less affected by the gauge problem. Again, going back to the original set of numbers that I've shown you before, now I have included the multi-wavelet results, And in black, you see the number of digits that we can guarantee are correct based on going to the next level. You see, this is 1,000, then 1,500, again 1,500, 1,570 something, 1,579. Okay, and the same here, the same here, and the same here. So this is a way now to show how good those calculations are. As you can see, when it comes to magnesium oxide and you go for Hartree-Fock, the first 3 calculations are complete garbage. But okay, that was in a sense reasonable to assume also given what happens later. But here, would you trust that 17,000 is the right number here? I wouldn't based on these values. But now I can, because now I can tell you that this is 1737. So this 17,000 is the right number. And 249, again, is the right number based on the values I get up here. So we can really benchmark what these shielding values are and how correct the Gaussian basis sets are. Okay, this is just again here we performed quite many calculations, and the original test set was due to the work from among the others Trygve and Kenneth. I don't remember all the other co-authors, I'm sorry. And we have they have triple, quadruple zeta, and then they also did some extrapolation. We perform multi-wavelet calculations. What you see by looking at these numbers that what we call MW3, which means 10 to the minus 3 precision, is reasonably bad, meaning it's worse than triple zeta. So in a sense, multiwavelet is good when you go to very high precision. Multiwavelet low precision is something to really avoid because it just gives you noise. But as soon as you go to 1 digit extra, to 10 to the minus 4, then you get better than quadruple zeta already. And MW6 means like 2 extra digits from that. That is now something we can trust as a benchmark. So we can use that number as a benchmark to benchmark both both the Gaussian type orbital, but also lower precision in the multiwavelet. So how many digits the others are giving us. So here I have collected some errors, so maximum absolute deviation, standard deviation, and maximum error for different functionals and different multiwavelet calculations. As you can see, multiwavelet 3 is garbage, so the errors are huge for shieldings. These are the errors of augmented quadruple zeta, so the order of 2 ppm with some outliers that are the order of 20 ppm. MV4, which is the one, better than quadruple zeta, is, you see, you have consistently smaller numbers here than you have for quadruple zeta. Then what we have done, we have also looked at the extrapolation methods with suggested values from the literature, and then we have also recommended a new value. We say, okay, if you want to do an extrapolation for a shielding, you shouldn't use 1.63, but use 1.05 because it gives better, much better performance. So you see, it doesn't really give you much more. So you see 1, 0.8, 0.8, so it's like roughly half the error you get with quadruple zeta. It's not much better. But here you get 1/5 of the error of quadruple zeta if you change. And this is just one parameter. For all molecules, that is some roughly 30 molecules and all the shielding for all the atoms in those molecules, and 5 different functionals including Hartree-Fock and Hartree-Fock. So it's one parameter only to bring you down from 1 to 0.3, 0.2. Okay? And this is the multiwavelet 5, which is the next best we can do just for comparison. So this value here becomes comparable now to this multiwavelet 5 more or less. This is the extrapolation formula we have used. And yes, this brings me to a conclusion. I think I'm very optimistic now with multiwavelets. There's a lot of things we can do. And it really shows that it has a potential. Not for everything, because there are some issues and some features that show where are the weak points. I'll tell you about this in a second. But what I really like is the fact when you do all electron calculations, then If you do multi-wavelets, you have only one inaccuracy in your calculation, which is your functional. So how good your calculation is depends only on which functional you choose, nothing else. So you have no basis set error anymore. Technical challenges abound. So memory, parallel scaling, so the size of the system is still a problem. Correlated methods are a huge challenge. People are working on it, not me personally. We are working on additional properties, solvent effects, and we would like in the future to include periodic boundary conditions, relativistic effects, and open-ended response. Coming back to the, I will conclude saying what the challenges I was telling you about is that our problem is that, as I was saying, we cannot rely on error cancellation. So whenever we have to perform a calculation where we have a difference between two large numbers, then we lose as many digits as that difference brings about. So if you have, let's say, a difference between two large numbers in which the first 4 digits are identical, then we lose all 4 digits. So we have a precision that is 10,000 times less than what it used to be. And instead, Gaussians are able to rely on error cancellation for these things. So I don't know yet how to solve this problem, so the only way I can see is that either one finds a way to calculate the same quantity without relying on a difference between two large numbers. Sometimes it's possible, sometimes it's not. Or otherwise, the only option for multi-wavelets is brute force as far as I can see. So increase the precision until you get enough digits. But that's not doable because all the time, because at some point you hit the limit which is due to machine precision. You cannot increase the precision indefinitely. Yes, with this I thank you all for your attention. I hope I didn't leave you like this guy. And yes.
All right, thank you, Luca. We're open for questions, and I think Trigger was first, so please go ahead, Trigger.
Very nice, but I have a few comments. First of all, I think you should be a little bit careful about the use of the word chemical accuracy, because it actually, it's never applied to absolute energies. It's actually applied to comparing with errors that you get experimentally.
Yes,
so it only makes
right.
sense, and also it only makes sense if you actually take into account all errors in your calculation, not just the basis set. There's nothing like a basis set chemical accuracy. It's the total relative to the actually true value, including correlation, whatever is needed, relativistic effects. I think that's a right use of that word. So it's perhaps a little bit misleading to use it for one part of this. But otherwise, yeah, it's just perhaps terminology. Then I wonder, what about how do you treat your exchange correlation? Are they actually also included in the multi-integration there? How is that?
I mean, we use XCFun.
Okay, but
use
what are the errors in XCFun?
What do you mean? No, I mean, we use XCFun, meaning we just give a density value and we get the corresponding functional. So
there are no errors in that? No numerical errors?
No.
Okay, so you have them to the same position as the rest of the calculation?
Yeah, exactly. Yeah. I mean, we were able to, at some point, we were able to see like a tiny difference between two different, this XCFun implementation, this libXC implementation, because the results were not exactly identical, and then that boiled down to a different definition of the LDA function. There was like some digits that were not exactly the same, or the implementation that I think was like a difference in the way the formula was implemented. So once that was corrected, also those differences leveled out. Coming back to your basis, to your chemical accuracy, you're right. I know exactly that that chemical accuracy is comparing to experience. What I want to point out is that we are at the point where a lot of algorithmic and technical errors are close to the inaccuracy of the calculation. So in a sense, when people start to say that, okay, this functional is able to give you chemical accuracy, I would like to be careful, because if you also have a basis set that have the same comparable error, so what is the error of the functional there?
Yeah.
So
I agree, but it's not correct to say that your error is chemical accuracy, because
I agree. I can reformulate that if you. Yeah. But what I'm trying to point out is that we are at the point where these kind of errors are significant compared to the errors we can achieve. Okay. So it's not that the algorithmic errors are much smaller than what the functional itself can provide. So when you then optimize the functional with a basis set that possibly has a larger error than the functional itself, you're not really doing any physically relevant work. You're just compensating errors. So your functional optimization is not doing any better physics. It's possibly doing you giving you a worse physics.
Just one more comment, perhaps. The PC sort of basis set, and you compare those with the Dunnings. Mm-hmm. And they perform better, the PC. One should be aware that Dunnings were never really developed for DFT. It's to actually cut the correlation energies for many body wave functions, whereas the PC were developed exactly to get these things used. So that's the reason. It's not because the correlation consistent bases have been poorly constructed. They were constructed for something else, and then people use it here. So that was some use for him.
Yeah. But it's true that they are at present they are possibly the most widely used set of basis sets.
Yeah, it's a great bonus, but that's not how they were constructed.
True.
All right, from the back bench in Oslo.
I like to hear. I would like to agree with people. I have been very irritated by the use of this term chemical accuracy, because it's completely arbitrary, and it relates to some thermochemical accuracy for this test set of GTOs. So I think it comes from the Popel camp. But I think in chemistry, your accuracy depends very much on your experiment. If you do photo detachment, electron spectroscopy, you can measure something by 5 valid digits and things like that, much better than this arbitrary 1 kilocalorie, which is also an obsolete unit. So for that reason, completely stop using it. But my question is completely different from this, and that is, you are using Cartesian coordinates blindfolded, essentially, just chopping up space and putting your wavelength functions. In a sense, it's a very nice and objective way of doing things, but in order to improve speed, would it be better than to take advantage of some of the symmetry, some of the local properties of the electron density function, because sometimes you are very far out and there are regions where nothing much happens, and you have the big problems, of course, at the very atomic center, as you discussed this problem. But except for that, the derivative of the density will be continuous, and could you do some kind of transformation of space, or could you do something nice in order to improve upon this scheme, taking advantage of what we know about molecules?
One thing that we are doing, and thanks to the fact that we have this adaptivity, is that you only refine when you need. So if I'll go back here, there. So you see what you are doing, if you assume that in this like sort of darker spot where you have a lot of refinement, a lot of smaller cubes, this is where the atom is, more or less. So where the cusp is, you actually refine very much. So it's not uncommon to go down 6, 7 levels. So which means that the size of your cube there is 2 to the minus 6 compared to the original one. Okay, so it's less than 100 than what you had before. So this is the adaptivity is doing this automatically for you. So far away, then you are most likely happy with this big cube. That is enough to represent your function. Additionally, something that we are not doing but somebody else is doing, you can take care of the cusp by sort of separating the orbital from the cusp and having this representation where you multiply cusp function by the orbital, and then you have like a smooth orbital times the cusp. This is what Florian Bischoff is doing, and yeah. And for Hartree-Fock and DFT for SCF calculation, it's not helping very much because it adds quite some overhead. But it seems very successful if you go for correlated methods. So if you go for MP2, then this helps also a lot.
I forgot to say that I like your talk very much. I forgot to say that.
Thank you.
All right, we'll move to Tromsø. Are there any questions here? Bingo, go ahead.
Well, because you show the table, you give different Gaussians and also different threshold for your wavelets. I know, okay, for wavelets, the Gaussian is you only change one parameter, you can get converged accurate results. But how about the efficiency of this Gaussian and the wavelet? I mean, if I use aug-cc-pCVQZ, I can get a similar result accuracy as yours, but it's much more efficient. Then I don't see the point to choose.
Yeah, what I said, I think I mentioned it briefly, is indeed the other way around. What we have seen doing this shielding and magnetizability calculation is that going one level down in precision, up in precision if you want, in the augmented, in the correlated correlation consistent basis set, so triple, quadruple, quintuple, makes the calculation 5 times lower. So it's a factor 5.
Yeah.
And that doesn't necessarily give you an extra digit on top. Multi-wavelets, going down one level, meaning getting 10 times as accurate calculation, costs you only twice as much. So in the long run, you win. Because there you just multiply by 5, and here multiply by 2. So, and so what we've seen, I don't have the numbers here now, but what we've seen is that for timings, for pure functionals, once we get to, I think, quadruple zeta and 10 to the minus 4, then we are more or less the same level. And the multi-wavelet is a little bit more accurate. 10 to the minus 4 is more accurate than quadruple zeta. But when you go to quintuple zeta and 10 to the minus 5, 10 to the minus 5 multi-wavelet is much faster than quintuple zeta. And it's way more precise on top. So there's really no point at that point to use Gaussians. We're not there yet when it comes to hybrid functionals. So as soon as you introduce Hartree-Fock exchange, we are way slower. But that's a factor. That's an overhead. The fact that one becomes 5 times slower every time and the other one becomes only 2 times slower is still there. But the starting point is a huge difference. So with pure functionals, we are able to win more or less at the level of quadruple, quintuple zeta. With hybrid functionals, you would have to go a couple of levels more in order to win. But I think we should be able to improve, or I'm optimistic that we can improve the efficiency of the hybrid scheme, and then we will get there as well.
Okay, so then according to your slide, my guess is the reason for wavelet you can win Gaussian is because Gaussian has cusp. It is the problem.
Yeah, the problem is the cusp. Yes, they are not as good as you would want at the cusp for the shield. The shielding, of course, is a tricky property for Gaussians. So, as I said, there are other properties. I mean, Stig now is trying with hyperfine coupling, and there again you end up with a calculation where you have 2 big numbers you have to subtract, and then you automatically lose all the digits that are identical in the 2 numbers. And if you have 4 digits that are identical in 2 numbers, it's a huge effect because you lose 4 digits of precision immediately.
All right, then I think we have 2 questions now, and those will be the final 2 questions. So Simon first.
Yeah. For the motion type calculations, do you apply any acceleration techniques like density fitting?
I'm not sure. I don't think so.
Because
I don't think so.
Of course, your comparison is not fully fair because you have these acceleration techniques that makes the the conventional calculation is much, much faster.
Okay. Yeah, I honestly, I cannot say. Most likely not. These are standard, I don't remember, but these are standard Dalton calculations, so not.
Okay, yeah.
And then Trigger.
Yeah, when you mentioned dipole moments, so on gradients, forces.
Gradients are fine, Hessians are not. Gradients are fine because we can use the Hellman-Feynman theorem.
Then, okay, how much noise do you introduce by that? Because you said like dipole moments, the array is linear in the area of the wave function.
Yeah.
Same with the gradient. You can actually include the response in the calculation of dipole moments, and then errors become quadratic again. Then you have to calculate the response to the field.
Okay, I didn't know about that.
Yeah, it's possible. All properties. The reason you get linear arrays is that you ignore the response, which is the zero contribution in precise theory, but not in approximate theories.
Okay.
So then you can make the area in the dipole moment quadratic in the area of the response and the wave function.
Yeah, but that would apply equally on the Gaussian side and on the multiwavelet side.
Yeah.
Yeah.
All right, so with this, I will encourage you to thank the speaker again. And have a nice weekend, everyone.
Yeah.